The problem with studying pattern formation is that patterns just keep repeating. But the brain is doing something that a pattern can't do, right? Which is it's processing information. And I just became absolutely fascinated with that. I studied computational neuroscience, working with Alexandre Pouget and Peter Latham and Wei Ji Ma.
You're a huge proponent of the Bayesian brain hypothesis.
Yes.
Why is that?
I believe it is the only right way to think about how the world works. You get some data, then you get some new data, and you sort of say, oh, how is it like the old data? And if it's similar enough, then you sort of lump them together, and then you build theories and you properly test hypotheses in the fashion.
Let's imagine we took all of the humans on the planet and we described them using this contextual reward function that you're talking about. It seems to me that that object would be one of the most sort of complex artifacts in the universe.
It's also the case that it's very difficult for me to figure out what your reward function actually is. A lot of work in behavioral economics has gone into trying to figure this out. But it turned out just measuring someone's reward function, which was a prerequisite for getting an AI algorithm that shares our value, is really impossible because you cannot disentangle belief and reward based on policy. If you don't know someone's beliefs, you cannot infer their values. If you don't know their values, it's also very difficult to disentangle their beliefs. So they disagree about a conclusion. They disagree about what action they're going to take. And if you don't want to resolve the argument, you of course instantly draw one of two possible conclusions. The person that I'm arguing with is either evil or stupid. They're stupid because their prediction engine, their beliefs are wrong, their prediction engine is wrong, or they're evil because their reward function is not the same as mine.
I'm Benjamin Crozier. I'm starting an AI research lab called Tufa Labs. It is funded from past ventures involving machine learning. So we're a small group of highly motivated and hardworking people. And the main thread that we are going to do is trying to make models that reason effectively and long-term trying to do AGI research. So one of the big advantages is because we're early, there's going to be high freedom and high impact as someone new at Tufa Labs. You can check out positions at tufalabs.ai.
They used to do experiments. They take the cat, you anesthetize it, you put an electrode in its brain, and then you show it pictures. And they initially were like, we want to find out what the neurons in the visual cortex are sensitive to. So they're showing it pictures of here's a mouse, right? Here's here's other things that they think cats, but here's a tree, a plant, a little food bowl, some water, all these things they thought a cat's neural or visual system should respond robustly to. And they found nothing, right? The neurons are just going, they're not making any noise at all. They're just not responding. And they were showing the cat images by just projecting onto a screen from a slide projector, right? An old, this is the 70s, right? Or I don't know what year it was. Slide projector where the way it works is, right, it drops a slide in, there's a light that shines through and it projects onto a screen. And these things, it's mechanical. So when it goes to switch the slide, pops that one out and it rotates and drops a new one in. And they're doing this experiment and they've gotten nothing. They have no idea what these neurons are responding to because they're just humming away at some low frequency. And one day, the slide projector breaks. And what happened is that, and I remember it was on the input or the output side, but basically a slide ends up not sliding in where it's supposed to be, but ends up going in cockeyed. And when that happens, what shows up on the screen is a big old white patch and a big old black patch, with an angle that's associated with the angle that the slide was at. And this happens, and it happened this one time while they had the electrode in the cat's brain, and all of a sudden the neuron that they were recording from just started going crazy, just absolutely bonkers. And so what did that mean? That means, that's what the neurons are actually sensitive to. They got this incredibly robust response out of the neuron when they presented this oriented thing. There'll always be problems. There'll always be mistakes. And for this reason, I don't believe we'll ever be in a situation where AI will be, executing plans and making decisions without any human oversight or advantage. Now, it may eventually get to the point where the only role, this is like everyone has their nightmarish view of the future. And it's Terminator's going to kill us all. My nightmarish view of the future is that humans are reduced to being, a bunch of complacent value function selectors, right? That their entire role, they've stopped thinking completely. They're just basically saying, yeah, that's good, that's bad, that's my contribution to society. I hope that doesn't happen. I hope that people, continue to think of AI as something that actually enhances their understanding of the world, And I'm definitely focused on building that kind of, a framework in which AI has the property that it's all about making people smarter, not about alleviating people from thinking.
Interestingly, there's work done on theory of mind analysis on LLMs, and that they appear to have some kind of theory of mind. You can give it
Okay, so
superficially, if nothing
oh
else.
my gosh, so I remember when the first, many years ago, when ChatGPT first came out, the first thing I did was I gave it the theory of mind test. There's this canonical theory of mind test, and kids who are about 3 and 4 and 5, like they can't pass it.
Right.
And then sometime 5, 6, 7, they acquire the ability to pass this sort of quote unquote theory of mind test. Dad and kid are sitting at the table together, and mom comes in and she puts the stapler in the drawer, and then she leaves the room, and then dad comes up and he grabs the stapler and he puts it in the cupboard, and then they ask the kid, and then mom comes back into the room, and then you ask the kid, where's mom gonna go to look for the stapler, right? Mom wants the stapler. Where's she gonna go look for it? And little kids say that she's gonna look for it where it is. I mean, duh. She's like, mom. She's like, she's omniscient, and so of course she's gonna go where it is. So that they're not able to solve the problem of seeing the world from the perspective of another person. They're not able to say, no, actually, mom didn't have that information. The dad moved the stapler.
Yep.
Right. And so right around 6 or 7, kids transition from not having this ability to having this ability, and we say that they have been past the theory of mind test. And I was giving this test to my kids about every 6 months or so. I was super curious. So ChatGPT comes out. It's one of the first early versions that you could just sort of start horsing around with. And so I sort of tried to give it just type chatting in a variety of theory of mind tests. And I was absolutely shocked when I forget out which perturbation of it was, I painted the scenario and asked it what the answer was. And it very cleverly responded by saying, that's the theory of mind test. Let me tell you all about it. And I was like, oh, okay. So you didn't pass the test. You were aware of the test.
Yes.
Right.
Yes.
And so to some extent, showing that an LLM can pass a theory of mind test, is fundamentally conflated with whether or not it knows what the theory of mind, whether it's already taken the test, so to speak, right?
Yeah, I can attest.
Shown the test.
I can attest that. I mean, my Keith, the co-host, there's this famous riddle. I think it's when John and Mary they both one. There are 2 numbers they have in their mind, and I think John knows the product and Mary knows the sum, and you have to kind of go through this all the possible combinations. And Mary says she doesn't know, and then John says they do know. But anyway, you ask that to ChatGPT, and it's like, oh yeah, this is the famous riddle. It's the sum and product riddle, and it gives you the answer 413. And obviously, if you modify it, you add an additional element to it, it's always going to just give you the canonical answer, even though it's wrong. And you say to it, no, that this is a variation. We've changed it. You need to think. You need to reason. I tried deep research. I tried O1 Pro. It just failed every single time.
Yeah, because it's overly focused on that very specific example.
Yes,
that is not generalizing well.
There is this thing that the way we've been describing all of this is that we need to have direct physical experience. And that's how epistemic foraging works. We just, we have direct physical experience, we compose things together. But we're a bit more sophisticated than that. We think, we have imagination. I gave you the TikTok example. Even language is about the propagation and accumulation of information without direct physical experience. It's one of the greatest things that ever happened to humanity. So, what is the role of just imagination, basically, when we create new knowledge?
Not create new knowledge, create new things.
Yeah.
Right. That's the last several hundred years have been one amazing technological achievement after another, and I like to think about how it is that we accomplish that, and was it inevitable? And I think that the answer is that it kind of was inevitable. We started out with this, we started out in this world full of objects, and we had to start modeling those objects and describing those objects. And we found that like partitioning the world into these things that are defined by how they interact was really convenient for prediction. But it also gave us a new skill. It gave us systems engineering for free, right? How does systems engineering work? Well, you have this system and this system, you have all these subsystems, and you have rules that govern how they interact with one another, which allows you to do what? It allows you to build something new, like Legos. Legos are great, this is not dynamic, right? But it's just like Legos. It allowed us to take these objects and put them and say, well, what would happen if I just stacked things this way, or I strung this set of, or I connected these objects in this new way? What would result? And what would result is something that is, you could, also call an object. That is sort of besides the point. But it does something new and interesting.
Yes.
Right.
Yes.
That's the kind of thing that I want that I want to see like AI start to be able to do. I want to see an AI that doesn't just sort of describe the world in which we live, but actually like is capable of doing stuff. I want to automate systems engineering. And the first part of automating systems engineering, right, is dividing the world up into subsystems, right, and the rules that govern their interactions. That's what makes it work. That's what allows you to take a bunch of simple things and put them together in a new and interesting way.
On the understanding thing, there are people who say that, it's not just representing the language, it's implicitly building a world model. So it's actually learning through the language, it's modeling things that go on inside your brain. And I can give you an example of me learning via a disembodied experience. I can go on TikTok and let's say my cousin is in Thailand or something on holiday and she's on the beach and she's doing all of these things and I'm not there. And I'm vicariously, I'm just like an LLM, I'm having that vicarious experience. What's the difference?
The difference is that you have something specific that's outside of the linguistic space that those symbols refer to. Right. So maybe you can't like explicitly imagine like the beautiful, it's like, oh, I've never truly experienced the beautiful white sand and the gorgeous sun and the calming waves, but you have similar enough experiences that were grounded in reality that you can extrapolate like what that experience would have been like. Right. It's all about being able to point. It really is about having those symbols meaning something specific and real. The manner in which you choose to represent the stimulus actually has implications for the neural code. So if you assume that its orientation, like as in it's literally angle, and angle is the thing that's being represented, then it supports one, then the evidence, the neural data supports one coding paradigm, right? And if but if you say that no, it's actually just feature intensity, where the feature in this case would be not the angle, but the actual waveform itself, right? And the intensity of the various different contributions of parts of that waveform. And now in principle, like there's a one-to-one mapping, right? Or not a one-to-one mapping. There's a mapping from the orientation, right, to this sort of other representation that's like feature intensity based. So there's a relationship between these two things, but which one of those two representations of the world you choose, right, ends up making different predictions about the world. So the issue ends up being like, choice of representation actually matters, right? And we like to phrase this in a Bayesian way and saying like choice of generative model actually matters. So if I have like this generative model and I say this is the brain's generative model, these are the underlying stimulus values or the aspects of the world that it's representing, then these are my predictions and they're great, right? It represents the same image, right? It represents the same thing out there in the world, but it's a different way of representing it. And then now the data is consistent with my theory. So choice of like the specific details, choice of representation, choice of generative model is the thing that ends up being what separates these two sets of predictions.
Yes.
This is sort of highly problematic because we don't really know what the generative model is that the brain is using. Like Ralph's is perfectly plausible, mine's perfectly plausible, right? They both represent the same class of images and things like that, but in completely different ways, and therefore make completely different predictions about neural data under these different coding hypotheses.
And one approach of that is, and I think you're going for this, line of sight legibility. So
right. So
yeah.
so if you had an algorithm that explained its reasoning every step of the way, right? You would get two things out of this. The first thing that you would get out of it is you would be able to understand like why it did what it did. You would incorporate that in your beliefs, and then you would benefit. You would benefit personally. You would be smarter because of the algorithm's outputs. And that's kind of what I want. Do I want smart computers? Yeah, but ultimately I just want to be smarter, right? I would like to know more. I would like to have an understanding of how the world works that's richer and fuller and better. And an AI that's just able to do prediction and make decisions, it's nice, but it doesn't really get me what I want, which is I want to understand what's going on. Now, that's the other thing that happens is that if you can analyze its decisions, or you analyze its line of reasoning.
I like this idea of thinking about language not as being an intrinsic representation of the world. There's the Shannon idea that it's actually encoding information about the world as a first-class representation, or the other approach is that it's just pointers, right? So we're all cognizing agents, and we only need this 10-bit stream per second of language because it's just a pointer to the same thing I have in your mind.
That's right. And so absolutely right, and that's one of the reasons why language does work. It works because inside your brain is a very, very sophisticated model of the world that is remarkably similar to the one that's inside my brain, right? Otherwise it would not work, right? Our brain, we have a common, you can think about this, we have a common grounding. Our cognitive, there's a common grounding of your cognitive understanding of the world and my cognitive understanding of the world. And it's that commonality is what allows language to work as well as it does. Where did that come from? What is the commonality? This is one of the arguments that comes out of like Max Ramstad and Carl Friston's like Bayesian mechanics work. The basic idea is that okay, so language works between us because our brains have a common grounding, right? They live in the same space. Like you can use words, and I can take my knowledge of how my brain works and use that to make assumptions about how your brain works, and then I can take that word, I can map it onto this rich set of cognitive things in my brain.
Yeah.
But where did that come from? What is the basis of that understanding? And the Bayesian mechanics argument is that it came from our experience, it came from evolution, it came from the world in which we evolved. The rich understanding that we have in our brains is a result of the fact that we live in the same, that is in common, is a result of the fact that we live in the same world, right? This is like the backhanded way of getting to an embodied intelligence argument. The only thing that makes communication possible is that we had to adapt to survive in precisely the same kind of environment. Maybe not exactly the same environment, but the same kind of environment. We had to develop, the cognitive tools that were necessary to do that. Otherwise, we wouldn't be here, right? We'd be dead. And that common grounding is what makes this rich communication possible. The basis of our understanding of the world is not linguistic. It's an understanding of the intuitive physics of the world in which we live. I remember this is why I hate talking about consciousness, and I try to avoid it. And I used to shut down conversations on the topic by simply saying, so what do you think of consciousness? Like, consciousness is the suboptimal way in which we perform reasoning when doing it correctly gets too hard, right? It's when we collapse our probability distributions. We say, no, it actually just works like this. Here's this real simple explanation. But that's what words are for. Words are for giving us simple explanations that we can convey to other people. But they are, in fact, massive simplifications of what our brain is actually doing, right? Now, if you take the functional region story about the brain very seriously, we have this little bit, here's language, it's over here, and it's a tiny part of our brain. It's not, it's the tiny part that we use to communicate with one another, but it's a very, very compact, lossy summary of what our brain is actually doing, which is something much, much, much more sophisticated. And you can think of conscious perception the same way. It's like, we know that people represent the world probabilistically for the most part, and yet we don't perceive it. Like, I perceive you're there, unambiguous, right? We don't perceive it that way because it's just too complicated, right? The brain is doing an incredible amount of processing that we are quote unquote completely unaware of, and our awareness is really just a compact summary of that is a poor representation of it. This is why we need to move away from language models, by the way. Language is an incredibly poor summary of what it is that our brains are actually doing, and language is an incredibly poor summary of the reality that it is meant to describe relative to the description of reality that's actually in our brains.
Certainly, when navigating romantic relationships, we do have language for all sorts of weird things. Even things like sour grapes and Schadenfreude, and there are many quite sophisticated, ambiguous situations that we have words for. Perhaps we have differential understandings of what those words are, but explore a little bit more what you meant by language and ambiguity.
The way I conceive of how we perceive the world is probabilistically. This is the whole Bayesian brain hypothesis situation. And it's very complicated. There's lots of things going on. We have this, we intuit a lot of this stuff. We have this intuitive notion of how the world works. But when it comes to compressing it down into language, our bit rate is tiny. Actually, who am I thinking of? There was a paper recently, Markus Meister. I got it. So Markus Meister put out this really great paper recently in which he pointed out that the amount of information coming into our brain is huge, absolutely massive. And he calculated the bit rate. I don't remember what the numbers were, but it was one of those things. It was a big number, right? And the amount of information coming out of our brain is like 10 bits a second.
Yep.
Right. So absolutely tiny, right? Well, one of the things that's coming out of our brain is like language. So we know that there's incredible difference between what's going in and like what's coming out. And there's a bunch of reasons why that might be. It might just be that our affordance space is like really small at the end of the day relative to like, our sensor space. And things like that. But one of the things that you can instantly conclude from this fact is that whatever it is that we are doing, it's an incredibly poor representation of our understanding. You can't just take actions and translate them into beliefs in a very easy way. When you have a situation where your beliefs are being formed by this massive onslaught of information, and our actions, which includes our words, right, are so limited. And so this is one of the reasons why, like, I don't think that like basing your model of the world or your AI model on language is the right move, because language is an incredibly poor representation of the reality as we must understand it in order to function in it.
Many folks, I mean, Stephen Piantadosi, of course, with his concept role semantics, he will argue that language models can understand. Now, they certainly seem to be capable of processing symbols in a way which makes sense to us. Right. And then there's the question of, well, at some point, mimicry, if it's correct enough of the time, there's no meaningful difference. But what would you say to people who really think that AI systems could understand?
Just don't. No. So prediction is so. Look, language models are very impressive, right? They're very good at like what they were trained to do, which is next word prediction, right? And you give them enough data and they can do it. They can produce like compelling, it seems as if it came from a person, right? And when you ask them for an explanation, they can come up with a compelling sounding explanation because that's what they were trained to do. But I wouldn't trust those explanations to be true, because effectively they've been trained to basically play a kind of like Mad Libs. You remember Mad Libs, where it's where you sort of put the noun here.
Yeah.
And so it ends up having the structure of an explanation because it was told what the structure of an explanation was, right? And it filled in words that made sense based on, which is great. So it can replicate things that it saw in its data, right? That in a way that seems plausible, but not in a way that I would say is necessarily correct, because it is just manipulating symbols. It is just looking at correlations. I'll believe that a language model is moving in the direction of intelligence when it can produce something that wasn't in its data set, right? And everyone says like, oh no, but it does zero-shot learning. There's no such thing as zero-shot learning, right? There's just stuff that was in your training data that you weren't explicitly aware of, right? And that's, which includes correlations between words. And so that's sort of my like high level response is that manipulating symbols can be compelling. It can look right. Doing, the ability to predict what someone would say is great.
Yeah.
Right. But it's not indicative of actually understanding. And that's because, again, we can go back to like, this is an embodied intelligence argument, right? It's because those symbols were just symbols. They're just relationships between the symbols. Right. And we can add vision, or vision language action model. And then so we're getting a little closer. It has some more of the flavor of something that would be embodied. But until a language model actually produces something like a creative insight, invents something new, I won't believe that it's intelligent. That's sort of my like.
Just for the audio, I was reading this great book, The Brain Abstracted, and she said, yeah, abstraction, ignoring details, idealization, something that scientists do, is deliberately distorting the truth.
Yes.
And yeah, so we can say the Earth, it's a sphere. It's not a sphere. It's just like all the other planets, they're spheres as well. It's an idealization. And Newton is still around. We still use Newton. That's an idealization, but it's very, very useful. But there are many scientific theories talking about these unobservable things like subatomic particles and things we've never seen before. And these are perhaps just blatant distortions of the truth. But it's very abstract, isn't it?
It is. I actually, the Newton example is a good is a good place to start, right? So there's a criticism of our intuitive understanding of physics, which is it's wrong. And so the classic example is that like, if I give you a bowling ball and a feather and you say like, well, what's and I say, I'm going to drop them. Like Newton says that like, they drop at the same space, which is like completely counterintuitive. So your intuitive understanding of physics is incorrect. Now that's not how I think about it. Your intuitive understanding of physics is totally correct because you've never seen a bowling ball and a feather dropped in a vacuum. Right? We don't do that experiment like in our everyday life, right? That's orthogonal to our experience is that no, they actually drop at very different rates. Why? Because the world in which we live doesn't include a vacuum, right? If we lived in a vacuum, then we would have a very different understanding and model. And then like our intuitive physics would be more closely aligned with like what Newton would say. So in this sense, right, our physics model was too simple. Right. So it's not the correct conclusion isn't our intuitive physics is wrong. Right. The correct conclusion is that the scientific model was too simple. Right.
With increasing sophistication of affordances or, connectedness to what's outside the boundary, there must be more representation, more modeling going on inside the boundary. And certainly in living things, we seem to see a kind of nesting of boundaries. Is that always the case? Because we're very sophisticated and we can do lots of things in the physical world, does that imply that there's a nested subsystem, or could you just have one big fat system which is just very good at modeling the world?
Okay, so so where you draw the biggest problem with the Markov blanket story is that it does not provide a definitive answer to the question of where should I draw my boundary. Right. So like when we do fluid dynamics, right, we always say that there's this prototypical fluid element. And whenever we draw it, it looks like a kidney bean, right? Because we don't know what shape it is and we're largely agnostic. We don't care. Right. Any partitioning of a glass of water into a bunch of fluid elements is completely arbitrary. Right. Yep. Now, you can still consider each one of those things as a Markov blanket, and then you can derive macroscopic equations from that, and it all works out just fine. The same thing happens within like the free energy principle, right? It tells you that like, if you draw a blanket, right, you can define an object based on the statistics of that blanket, but it doesn't tell you where to put it. Like I could draw a blanket all the way around Tim, right? Or I could, put one on your arm and one on your, wrist and all of these things are acceptable partitionings of your system. This was the problem that I was working on when I was still back at Duke, was trying to figure out like, how do you actually select the right partitioning of your system? How do you divide the world up into parts and pieces that makes the most sense? Now, I would say I have an answer to this problem. I will not be saying, however, it is the right answer or the best answer. It is a answer. In the traditional approach to the free energy principle, they took the definition of a Markov blanket was more aligned with the statistical definition, right? I pick an element and I say, well, what's the blanket of this element, right? And I'm going to pick one because, like, oh, maybe, you know, it's like, I don't know, maybe it's in a region of high density, or how you pick is arbitrary. Every element that you pick, like, has a blanket. And the way that they originally made decisions about where to draw their blankets was just by basically saying, well, I know it's going to have a blanket, so I'm just going to find all the things that it bumps into and interacts with, and then I'm going to keep expanding that blanket until I get something that that captures all of those interactions, right? So I like to think of it as, you know, you've got a bunch of stuff, but these guys, you know, the guys inside are all tightly coupled. They never, throughout the entire course of the time evolution of the system, these guys never interact with these guys over here, right? And so I can sensibly draw a blanket based on this sort of long-term estimation of the adjacency matrix of the system. So I can look at, like, who's interacting with who at any given time, you know, just average that, just sum them all up, get one big effective adjacency matrix, and then I can just sort of divide that and then pick a node and say, well, what's the smallest, you know, isolated cluster of interactions? That becomes the internal states. You know, and then it has a boundary because it has to, right? Because that's what allows you to segment. Now, systems that don't have blankets are like, you know, water molecules that are just bouncing off of each other and are constantly mixing and interacting.
There are folks who are science realists, and I guess that's a form of Platonism where basically you think the universe is written in code. And the code is legible. You know, if only we could find the code, then we know how the universe works. And the other school of thought is that no, actually, we do have these very idealized models. We can model pockets of regularity, and then there's a load of noise. And we decide as scientists that the noise is acceptable. Like, you know, the noise doesn't mean anything. It doesn't add any value. It won't ever be useful to somebody else.
I mean, noise is in fact simply how we model we model either ignorance or shit we don't care about. Right? That's what noise is for, right? It is a model of ignorance or a model of something you've decided is irrelevant to the current situation, right? These are design choices, though, when we design our theories, right? We identify the domain in which we want the theory to operate, right? And we decide what it is we care about and what we don't care about. Often, like certainly in the lab, right? You know, these well-controlled experiments because you know you don't want to deal with all the complexities of the real world. And that does induce biases in the theories that we discover, right? And it's like the neuroscience example where we've been showing Gabor patches and moving gradients for far too long, and that actually has created a bias in our understanding of how the brain works. You know, is there a mathematical system or set of equations or laws of the universe that are true and discoverable?
Yeah, I mean, do you think that is the case, and do you think they would be legible?
So I remember I was giving a talk at one point, and a student asked, so I'd been talking about, like, you know, it was talking about variational inference and how you have your approximate posterior distribution and you have like your ground truth distribution and you're trying to find it. And a student asked, is there a true P? So P was what I was using for like the ground truth distribution, which was done for convenience. It's like, is there a true P? And my response was to simply say no. Now, it was done in part in jest, and also because I just didn't want to answer the question, because there must be, in a sense, like reliable statistical regularities in the universe, right? If there weren't, we would not be having this conversation. Now, you know, is the precise nature of those statistical regularities discoverable? Maybe. But it's kind of irrelevant, right? We know that you know, so in the sense, like, is there a true P? Yes, there probably is, because if there weren't, we wouldn't be having this conversation, but I don't know what it is. And I'm not entirely certain that it's discoverable.
But even then, is there a hierarchy? There's a strong statement, which is that there is no ontological epistemological divide, you know, that we can actually build a model that just models the world as it is, you know, not some lossy abstraction. the sort of deflationary, the weaker version is there are regularities in the universe, and we can build models with very significant predictive power of those regularities.
Right. But are they true? That's the question I believe the student was attempting to ask. That's the question that I'm trying to figure out if I'm being asked now.
Wouldn't it be false by definition? If you're not modeling everything, wouldn't it be false by definition?
Yes, it is false by definition, right? There's like, this is, I like to say that a proper Bayesian places no metaphysical significance on the parameters and latent variables of their models, right? It's always the case that there's other models that haven't been explored that may be better. And there's other, unless you have some sort of exhaustive procedure for model generation and testing, which we don't, there's no way you could even conclude that one of them is the best. Right?
Well, this brings me to the next thing, is my co-host Keith Duggar, he's a massive Bayesian, and he loves saying all knowledge is conditional. And I was reading my notes. You say exactly the same thing, but that rather leads to this quite constructivist idea, not the strong sense, where everything is just like, fictitious, if you like, but our knowledge of the world does depend on the questions we ask and the tools we use and previous discoveries and so on. And that rather lends, it begs the question whether some of these foundational theories, even like the free energy principle, whether they are actually true statements about the universe, or they're just one perspective of many.
They're one perspective of many. The free energy principle is not a theory, right? It's a mathematical principle. I mean, at the end of the day, it's like Jane's max cal, right? Or max ent, right? Coupled with the Markov blanket notion that basically says the world can be sensibly segmented into useful parts and pieces. But that's all it is. It's a mathematical principle. It's a way of guiding how you create your models that I believe is very sensible. But it's not an actual like theory. It is a mathematical framework. And I love mathematical frameworks. They're great. They constrain your theories, and if they're good frameworks, they constrain them in sensible ways. But they're just theories. And that's what a proper Bayesian would always say. You've got a model, it's just a model. It might be a very good model in terms of its ability to do prediction and data compression, but it's just a model.
We can build an AI model today that does a really, really good analytical job, and it will never be legible to us.
A lot of times, all you care about is like predicting what are the consequences of various actions that you could have performed. This is the prediction. You may not, in fact, care about the explanation. You may just sort of trust that it's like, well, it's been validated. It's, I've done all of the math. I've done all the checks that I'm supposed to do, and I'm just going to continue to trust it. I don't see a real problem with that, but I find it very unsatisfying, right? I would like to understand, what's going on. But the reason I would like to understand what's going on is because if we start putting these algorithms in charge of making decisions for us, right, we are presuming something that is really hard to do, that is really hard to demonstrate, and that's that they are making the decisions that we otherwise would have made. This is what alignment is all about. In an ideal setting, you have this like high res, like super smart AI, does amazing prediction algorithms, and it makes all the decisions, and based on those predictions, it makes all the decisions for you, right? And does so in a way that's consistent with your values. That is a necessary prerequisite, in my view, for determining whether or not the AI has your values. Right. So this is the biggest problem that I think we have with AI as it currently stands. Right. In an RL setting, right, you have three things. Right. You have your prediction engine, and I think we can argue that machines have much better in certain domains have much better prediction engines than we do, and arguably we can expand more data. The prediction engines that they have will be significantly more precise than our own, right? And this is true for like physics prediction engines, are also like, it's the same sort of thing, right? Our intuition has been replaced by these formal physical models, right, that do a better job of predicting the outcomes of experiments than our like naive intuitions, right? So you got a prediction engine. You have your reward function, which basically sets your goals and determines your, and represents the values of the system. And then you have your action selection, your policy, right? And the policy, and in most of RL, right, is all about figuring how do I compute my policy, right? Given my predictions, right, and my values. But that's the whole point, right? Is prediction plus value equals policy. Now, when we start just trusting AI algorithms, what we're really basically saying is that we're trusting them to execute a policy that's consistent with our reward function, right? But with a better belief model than ours. Right, that's the goal. The goal is like it's able to do better prediction than we possibly could. It has the same reward function as we would. So based on those predictions, it's making decisions in the same way that we would, but then its policy ends up being better or more effective at achieving that reward. It's not impossible to have an AI system that does go through this process of identifying our values to some extent, but it will never be perfect. It'll always be the case that it will have an impoverished view of our reward function. It will have an impoverished, because there's no way it could really hammer down precise knowledge of our belief formation systems. It could get a pretty good one, and from that, it could be trained to estimate reward functions.
Because there was that famous "Reward is not enough" paper by "Reward is enough" paper by Sutton.
And he's absolutely right. If we could write down the right reward function, I think that to some extent that's true. That would solve a lot of problems. Here's the question though: what's the right reward function? How do you compute that? Where does that come from? Why is do we even have the same reward function? Probably not.
Probably not.
Yeah.
Yeah. So you're saying let's imagine we took all of the humans on the planet and we described them using this contextual reward function that you're talking about. It seems to me that that object would be one of the most sort of complex artifacts in the universe.
Quite possibly. I mean, we could just average them all. It's just voting. No, it's not a question of like what to do with what to do about. In my view, it's not a question in terms of what to do about the fact that people have different reward functions. Take a utilitarian. I'm no problem with that. Take a rank utilitarian approach, just average it. The real question is, what is your reward function? Like, if you could write it down for me right now, then that'd be great. I'd love to see you try. No, it's really difficult to get people to express their reward functions in a way that can be translated neatly into the language a computer can understand. I do believe that we kind of do sort of have something that resembles a reward function. I don't like to talk about it in terms of reward functions. I like to talk about it in other terms. But let's just, like, for the sake of argument, let's just go with that. So where does your reward function come from, and how do you represent it, and what is it? How do I get access to your reward function? Because if I want to replace you with a robot, I don't want to replace you with a robot. But if I wanted to, right, that's something I would need to do. I would need to be able to figure out what's your belief formation mechanism and what's your reward function. And it turns out that, like, it's really difficult to do that. In fact, I'm going to argue that's impossible. So not only is it the case that there's no normative, well, barring divine intervention, there's no normative solution to the problem of reward function selection. There's no, like, that's the right reward function, right? Not only that, right, that there is no, like, right or wrong reward function that you can obtain just from data. It's also the case that it's very difficult for me to figure out what your reward function actually is. A lot of work in behavioral economics has gone into trying to figure this out. And every time they do, they keep finding these, like, weird things that happen. And some of them have really sensible explanations, like, oh, it's because it's context dependent, or, oh, but it turned out just measuring someone's reward function, right, which was a prerequisite for getting is a prerequisite for getting an AI algorithm that shares our values, right? Is really impossible, because you cannot disentangle belief and reward based on policy, right? So if I'm just if I take an action, and I'm a rational maximizer, and I take an action, and it is a product of my reward and belief, and then there's like an argmax operation. So there's a convolution, right, between reward and belief, right, followed by an argmax operation. But you only observe the action.
You can't then deconvolve.
Yeah. How do you? Yeah. So you can't go backwards, right? If you don't know someone's beliefs, you cannot infer their values. If you don't know their values, it's also very difficult to, like, disentangle their beliefs. But for certain, right, without knowing somebody's beliefs, you cannot infer their values. When two people are arguing, they disagree about a conclusion. They disagree about what action they're going to take. And when you want, if you don't want to resolve the argument, you of course instantly draw one of two possible conclusions. The person that I'm arguing with is either evil or stupid. They're stupid because their prediction engine, their beliefs are wrong, their prediction engine is wrong, or they're evil because their reward function is not the same as mine. That's the lazy thing to do. Now, if you're actually trying to have a productive argument with someone, what do? You start talking about like beliefs. So, well, why did you come to that conclusion? Why was that the right action? And then someone will say, well, it's because, here's the list of facts, and then here's the predictions that I'm making based on those facts. And then you argue about whether or not the predictions follow from the facts, right? Or you argue about like missing facts that they should have included that they didn't when making their prediction, right? So what are you doing there? You're sitting there and you're having a conversation in an effort to determine the other person's belief formation mechanism. Once I have, in my mind, an understanding of your belief formation mechanism, then and only then can I finally infer or get a good estimate of what your reward function or value function actually is.
How could we build aligned AI systems? Because even, I'm sure like Tesla, they're recording lots of situations where people are running over rabbits and stuff like that. But fundamentally, though, there's a real sparsity, because I think those really important situations might be underrepresented or not represented at all. Many approaches to aligning these predictive, stochastic systems is, okay, let's have a meta model, which we have guardrails and we apply rules and so on. Or do you think we could actually incorporate it into the base system itself? And how would we do that?
What we'd like is it would be very awesome if we could actually figure out what our reward functions are and like get them into our AI agents. That's really challenging. I think that the only way that we're going to ever get anywhere close to that is if we build an additional layer into our sort of into our AI algorithms. It's an additional layer that explicitly models my beliefs, right? That probes that engages in the conversation that I proposed earlier, where you and I are talking and we disagree, and so we sit down and we talk about, well, what are the possible reasons why we might have disagreed? Right. And in the process, you and I each form a model of the other person's belief formation system. Right. And then to the extent that that's an accurate model, right, we can then conclude that any differences are difference in reward functions. And so if we wanted to become aligned, right, one of us is going to have to, it's going to be you, by the way, one of us is going to have to change our reward functions if we want alignment, once we've gone through that process of agreeing on a belief formation mechanism.
I see. Jeff, thank you so much for joining us today.
Absolutely. Thank you.